Welcome to Hart und Trocken. My name is Dirk Schiborn, and in this video we talk about integration by substitution. Integration by substitution is a special way to integrate certain functions which have a special structure. How exactly that special structure looks like and how exactly integration by substitution works, I will show you detailedly in this video. So, have fun and let's go! To understand what integration by substitution is and how we can use it to solve integrals, we look at the first motivating example. We want to calculate the indefinite integral of the function x squared plus 1 to the power of 100 times 2x. In fact, we could solve this integral by brute force. We could expand the 100 factors x squared plus 1, which would involve a lot of work, but a computer could do that. However, doing that calculation manually would take a long time. But there's another way to do that, by substitution. By substitution means, in this case, we substitute the expression x squared plus 1 by a new variable, say u. Then we don't have x squared plus 1 to the power of 100, but we have u to the power of 100. Interpreting u as the new independent variable, it is easy to find an indefinite integral for the function u to the power of 100. As u is the independent variable, we have to modify the integration variable accordingly. So we have du instead of dx. Now remember, finding the indefinite integral is nothing else than finding all antiderivatives of u to the power of 100. We find that the indefinite integral of u to the power of 100 equals 1 over 101 times u to the power of 101 plus c. Now we take this function and resubstitute u to be x squared plus 1 again. We call this function h of x. I now claim that this function h of x is the solution of our original integral. In fact, it is easy to verify this result, because we simply have to differentiate h of x and check if we obtain the original integrand. So that is 1 over 101, and then we have x squared plus 1 to the power of 101. And that is a composite function. That means here we apply the chain rule. The outer function is, well, to the power of 101. So the derivative of this outer function is 101 times the inner function to the power of 100. And then we have to multiply by the derivative of the inner function. And that is 2x. So if we simplify, we have exactly what we want. So, well, the question is, why did that work? That means, how can we recreate such an elegant way of solution? Well, let us try to be smart and look for features in our original integrand which made that procedure possible. The first feature is that there is a composite function involved, with an inner function and an outer function, just as we know it from the chain rule for differentiation. But then there's another aspect, and that is the expression 2x. What is 2x in this case? Well, if we look to our verifying by differentiating using the chain rule, we have found that 2x is the derivative of the inner function, one important ingredient of the chain rule. Now maybe it is important to have this derivative of the inner function as a factor in our original expression. And in fact, yes, that is exactly the structure we need. Composite function times derivative of the inner function. If we have this beautiful situation, we can apply a beautiful rule which is called integration by substitution. Now, as always in mathematics, we look at two aspects of the topic. The first one is to build a general argumentation why this method works for certain functions. That means we want to prove it on a very general level. That is actually what mathematics is all about. Then the second aspect is to develop the ability to identify situations where we can apply integration by substitution. That is not always easy to see, because even though we might have understood the general principle, it is not at all easy to see when we have a situation where we can apply it. So this is something where we need to get trained in. However, being a mathematician, I would love to start with a general proof. So please stay with me and watch the arguments carefully. We start our general argumentation with two functions, f of x and g of x. We further assume that we have an antiderivative of x, which we call capital F. We also assume that g is differentiable and that we have the derivative g prime of x. So that is our general setup. Now we start the argumentation. We first note that because capital F is the antiderivative of f, we have that the derivative of capital F is f. In the second step, we define a new function. We call this function h of x, and we defined it to be capital F of g of x. In particular, h of x is a composite function. In our third step, we calculate the derivative of h of x. Because h of x is a composite function, we apply the chain rule to find the derivative. According to the chain rule, we have f dash of g of x times g dash of x. That is the chain rule. Now, because of number 1, that means because the derivative of capital F is f, we can replace capital F dash by f. In the fourth and the last step, we want to calculate this indefinite integral. Remember that calculating an indefinite integral translates to the task that we have to find all primitives or all antiderivatives for the integrand function. That means we want to find all antiderivatives for f of g of x times g prime of x. Now, using what we have found in number 3, we can replace the integrand function by h dash of x. So again, what does that mean? Well, it translates to the task that we have to find all antiderivatives for h dash of x. But because h dash of x is the derivative of h of x, which has been defined in number 2, we have already found one antiderivative of h dash, namely h of x. And because we're supposed to find all antiderivatives, we add an additional constant plus c. Now we do the last step, because according to number 2, h of x equals capital F of g of x. So we replace h of x by this expression. And there we go. This is the general result I wanted to find. So let's summarize this. This equation, or this rule, is what we refer to as integration by substitution. As you can see, and as you already know by our initial example, this rule helps us to find the antiderivatives for functions of a very special structure. And this very special structure is given by f of g of x times g dash of x. If we rephrase this, in other words, if the function consists of the product of a composite function, which is f of g of x, and the derivative of the inner function g dash of x. Whenever we have this situation, we can directly apply the equation and calculate the antiderivative of the outer function, capital F, and plug into that antiderivative of f the inner function g of x, add an additional c, and we are done. Now let us breathe some life into this equation by looking at several examples. In our first example, we want to calculate this integral. As we will see, the integrand function is perfectly tailored to fit to the integration by substitution formula. Because at first we note that there is a composite function where the inner function g of x is x to the third power plus 4x plus 5, and the outer function f is, well, take this inner function to the sixth power. And what is very nice and convenient here, the derivative of the inner function, g dash of x, is nicely present as a second factor. Admittedly, example functions like these are deliberately tailored to fit to the integration by substitution formula, and usually we don't find them in a nice form like this in practice. However, let us not worry about practice and solve this example. Remember that the integration by substitution formula gives us this equality, where g is the inner function, x to the third power plus 4x plus 5, and capital F is the antiderivative of f. So we need to calculate that antiderivative. We do this by using a variable different from x, typically u, and calculate capital F of u as the indefinite integral of f. Now, in this case, f is u to the power of 6, so we replace f of u by u to the power of 6. This can be easily calculated to be 1 over 7 times u to the power of 7 plus c. Now we use this result to obtain our final result by plugging in g of x for u. Let's do another example. We want to calculate the indefinite integral of a rational function, 3x squared plus 4x plus 5 divided by x to the third power plus 2x squared plus 5x plus 8. Now, do you see any inner function, any outer function, or any derivative of an inner function? Well, you see that the situation is quite different than in the example before. In the example before, both the inner function, the outer function, as well as the derivative of the inner function were quite obvious. Here it's not that obvious, but still there's one thing which is very obvious and which is actually the clue for dealing with this integral. And this is the fact that the numerator of this fraction is exactly the derivative of the denominator of this fraction. So there seems to be something like an inner function and its derivative. To make that more obvious, we just put the derivative as a factor next to the fraction. So we have this. So the bracket on the right-hand side is the derivative of the denominator. So the denominator must be the inner function g, and the bracket must be the derivative of g. So what is the outer function? What is f? Well, it is 1 over the inner function. That means f of u is 1 over u. So we have to find the antiderivative of f of u. But that is easy because 1 over u is an elementary function and its antiderivative is ln of absolute value of u plus c. So we take this antiderivative and plug in g of x instead of u. And we have the solution. Again, let me note, to have an integrand like this, which has exactly this structure, well, that is not very likely. If we change just a little thing in the original expression, for instance, if we replace the power of 2 in the numerator by 3 or something else, things don't work out anymore. Simply because the numerator is not anymore the derivative of the denominator. So you see that in order to be able to apply integration by substitution, we really have to be lucky. Let's do another one. We want to calculate the indefinite integral of the function sine x times cosine x. As in the previous example, there is no obvious composite function. However, and that is important, there is one component of the expression which is the derivative of another component. Namely, cosine of x is the derivative of sine x. Consequently, that looks like that sine x should be the inner function g and cosine of x should be its derivative, g prime of x. However, what is f? That is, what is the outer function? Is there any outer function? It doesn't look like that there is any outer function. However, even there is no obvious outer function, there is one special function which we can always wrap around g of x. That means that we can wrap around sine of x in such a way that sine of x stays sine of x. And this function is the identity. That means the function f of u equals u. This function has just no effect. If I plug in g of x into that function, we will obtain g of x from that function, with no change at all. So yes, using this function f and using sine x as the inner function g, we have exactly the structure we need to be able to apply integration by substitution. And that is, just to remind you, this structure. Now, as in the examples before, we have to find an antiderivative for the outer function. That means we need to calculate this indefinite integral. And that is easy to solve. We get 1/2 times u squared plus c. And finally, as usual, we replace the variable u by g of x, and we are done. By now, we have used integration by substitution to calculate indefinite integrals. However, we can almost as easily use it for calculating definite integrals. That means for calculating areas under curves. The only thing which is different from using it for indefinite integrals is that we have to take care for the limits of the integral. Let me show you what I mean. We start by writing down the integration by substitution formula we have used for indefinite integrals. Remember, this formula only works for functions which have a very special structure, namely the structure which fits to the template on the left-hand side. Let us now modify the integral on the left-hand side by adding the limits a and b to the integral. Consequently, the right-hand side is no antiderivative function anymore, but it is the difference of the antiderivative evaluated at b minus the antiderivative evaluated at a. Remember that that is exactly the way how we defined definite integrals. If we want to calculate the definite integral from a to b of a given function, take an antiderivative of this function and take the difference of the evaluation of this antiderivative function at b minus its evaluation at a. Now we take the expression on the right-hand side and do a little reinterpretation, because now we don't think of a and b to be the limits of the integral, but of ga and gb to be the limits. So let me color this accordingly. So nothing changed here except for the colors. Now observe that we know that capital F is the antiderivative of f. So applying the definition for definite integrals once more and in the reverse direction, we get this expression. And we can summarize what we have just done in the following rule. The value of this formula lies in the fact that in certain cases it can help us to transform integrals of the structure of the left-hand side into the much easier structure of the integral on the right-hand side, but, and that is important, we also need to transform the original limits of the integral from a to g of a and from b to g of b. Let me show you some examples. We want to calculate the definite integral of the function x times e to the power of x squared with the limits 0 and 1. As in the previous examples, we first try to match the function x times e to the power of x squared with a structure which we need for the formula for integration by substitution, which is this one. So once more, we have to ask ourselves, is there an inner function, is there an outer function, and is there the derivative of the inner function? Well, in this case, we clearly have an outer and an inner function. namely the inner function x squared and the outer function f of u equals e to the power of u. Because in this case, the expression e to the power of x squared is nothing else than f of g of x. However, what about the derivative of the inner function? That means the derivative of g of x. Well, the derivative of g of x is 2x. However, we don't have the factor 2x in our function. We only have x. So, is that a reason to give up and stop trying to use integration by substitution? Well, no, it is not, because the idea is to modify the integrand function in such a way that we have the situation we need, while at the same time undoing this modification. Let me show you what I mean. If we had an extra factor 2 inside of the integral, like this, we would be happy, because then 2x is exactly the derivative of the inner function x squared. And we have a perfect matching with our template. However, the factor 2 is missing in our original integrand function. But this doesn't matter, because we can simply undo this modification by multiplying the integral by 1/2. We simply have to make sure that we keep this extra factor 1/2 in the following calculations. So now we are ready to apply the rule for integration by substitution for definite integrals. According to the rule, we first have to find an antiderivative for the outer function f of u equals e to the power of u. In this case, that is very easy. An antiderivative is e to the power of u itself. So, according to the rule, our integral equals this expression. Watch that we have kept the factor 1/2 and that we use the new limits g of 0 and g of 1. If we now replace f of u by e to the power of u and calculate the limits, we get this expression. Observe that effectively the limits didn't change, well, because g of x is x squared and 0 squared is still 0 and 1 squared is still 1. So in this case, nothing changed. Now, using the definition of this notation means that we have to insert the upper limit and the lower limit into the antiderivative and calculate the difference. And if we simplify e to the power of 1 to e and e to the power of 0 to 1, we have this final result. Let's do a last example. We want to calculate the definite integral with the limits 1 and 9 of the function square root of x minus 1 to the third power divided by square root of x. As always, we look for the inner function, the outer function, and the derivative of the inner function. In this case, we have obvious candidates for the inner and the outer function, namely square root of x minus 1 for the inner function g of x, and f of u equals u to the third power for the outer function. So the entire numerator contributes the expression f of g of x. To make this even more obvious, let us rewrite the integral while writing numerator and denominator next to each other. So far so good. But now, again, as in the previous example, the question remains, what about the derivative of the inner function? Okay, so let's calculate this derivative of the inner function, g dash of x. This derivative is 1 over 2 times square root of x. So, as in the previous example, we don't exactly have that derivative of g of x as an extra factor in our integrand function, because the factor 2 in the denominator is missing. In other words, the factor 1/2 is missing. But as we did it in the previous example, we can create the situation we need by modifying the integrand function while undoing this modification at the same time. So we can rewrite the integral like this. Observe that in the integrand function, I have created the situation we need by adding the factor 2 into the denominator. And at the same time, I have undone this modification by adding the factor 2 in front of the integral. So these two factors too cancel out, and effectively we have the same integral as before. But the good thing is, we now have the perfect match to apply integration by substitution. In order to apply it, let us find an antiderivative for the outer function f of u equals u to the third power. This is easy in this case. The antiderivative is 1/4 times u to the fourth power. Now, the next step is that we take this antiderivative, put it into edgy brackets, and equip it with the limits. And of course, we must not forget the extra factor 2, which we need to undo our earlier modification. Next, we calculate the limits. For this, we remember that g of x, the inner function, is square root of x minus 1. So if we plug in 1 into square root of x minus 1, we get 0. And if we plug in 9 into square root of x minus 1, we get 2. So we're now ready to plug in these limits into the antiderivative, and we receive this result, which, if we simplify, equals 8. So that is the value of our original integral. So that's it for this video on integration by substitution. Thanks for watching and see you next time.